YouTube. My name is Manny and welcome back to the channel. In today's lesson, we're going to be talking about exponents, right? More specifically, laws of exponents. We're not going to be doing any exponential expressions or exponential equations. We're just going to be elaborating on exponential laws and just talk a bit about them and basically how we can use them to solve obviously exponential equation and expressions, right? But before we start with exponents, I really want us to start by breaking down the anatomy of an exponent, right? So there's certain terminologies that we're going to be using when we talk about exponents, and hopefully with this anatomy you'll be able to kind of pick up with the terminology when we start discussing the laws. So we have a here, right? And let's say this a is raised to the power of m, right? So in contrast, a is what we call a base, right? Or let me just try to use a different color. A is what we call a base. So our a is referred to as the base, and obviously our m is what we refer to as the exponent. And the combination of the two is referred to as the power. So how we normally call this out, we'll say a, the base, to the power everything of the exponent, right? So that's just basically it when it comes to the anatomy of an exponent. You'll hear me saying that a lot, so I just really wanted you to get to understand what I'm basically saying before we talk about the laws of exponents. So let's start. So the first law says if you're multiplying powers, so in this case we'd say a to the power of m multiplied by a to the power of n. So if you're multiplying powers, which is everything that have the same base, what we do is we add the exponents, right? So that would be m plus n. So if you're multiplying powers that have the same base, we add the exponents. If they don't have the same base, we obviously don't have to add the exponents. So let me give you a numerical example so you kind of get to understand. So let's say, for example, we had something like 2 to the power of 2 multiplied by 2 to the power of 3, right? We know 2 to the power of 2 is 4, multiplied by 2 to the power of 3 is 8, and 4 times 8 will give you 32, right? In this case, we don't have to go through that process of obviously expanding. The only thing that we have to do here is say 2 to the power of 2 plus 3, right? And with that, we have 2 to the power of 5, right? And 2 to the power of 5, we know if we simplify that, we'll get 32. If they say we need to leave it in exponential form or to its prime factors, we're just going to write 2 to the power of 5. But obviously, if we have to simplify it, we'll write the final answer, which is 32, right? So that's basically what you're supposed to do when you're adding exponents. But let's say, for example, we're given something like a to the power of m plus 2 multiplied by a to the power of minus n. Right? How do we handle this one? Same concept. If you're multiplying powers that have the same base, you add the exponents. So what you're going to do in this situation, you're just going to say a to the power of m plus 2 plus minus n, right? And obviously, if you solve that, you're going to have a to the power of m plus 2 minus n, right? Since this plus, when it multiplies with the negative, you'll get a negative value. So that's basically what the first law says. So now let's get to the second law. So with the second law, it's kind of like the inverse of the first law. What I mean is this. So with the second law, we're saying if we're multiplying powers, not actually multiplying, if we're dividing powers that have the same base, we should subtract the exponents. So if we have a to the power of m divided by a to the power of n, we're supposed to subtract the exponents, and we're going to get the answer. And a numerical example, we're going to use the same example. Let's say we had 2 to the power of 3 all over 2 to the power of 2. That will give us, obviously, that will give us 2 to the power of 3 minus 2, which is 2 to the power of 1. And obviously we know 2 to the power of 3 is 8, divided by 2 to the power of 2, which is 4, and 8 divided by 4 still gives us 2. So it still works when you use a numerical example, right? But what if in that case we have two terms? So what I mean is this. Let's say we had a to the power of m all over a to the power of n minus 2. So what do we do in this case? You're still going to use the same law. So in this case, we're just going to say a to the power of m minus. So since we have two terms that we're going to be subtracting in the exponent of this a here, we should put a bracket because this negative right here is distributed amongst the two terms. So we're going to put a bracket to show that that negative obviously multiplies on both terms, right? So we're going to say a to the power of m minus n, and obviously negative multiplied by negative will give us plus 2. So that will be your final answer. So keep in mind with that, if it's two terms, always put a bracket around them. Obviously, if it was if you were multiplying these two terms, this would have been a plus, and a plus obviously won't have an effect on the two terms, so you don't really have to put a bracket. But get accustomed to putting brackets because it's a mistake I commonly see amongst a lot of students, right? So yeah, let's jump to the third law. So with the third law, let's say for example we have two different powers, right? In this case we have a and b, a to the power of 1 and a b to the power of 1 multiplying each other, and around them or outside the brackets we have an exponent that's multiplying what's inside the brackets. So in this case, what we will do is we will distribute the exponent amongst the two bases, right? We'll distribute the exponent amongst the two bases. So our final answer will look something like this. We'll say a to the power of x multiplied by b to the power of x. So that's basically how that one goes. While we're still on that note, law number 4 is kind of the same, right? So with law number 4, if let's say for example we have two powers or these two terms obviously dividing each other, and we had an exponent there, this exponent will distribute it amongst the numerator and the denominator. So that will be a to the power of x over b to the power of x. So that's basically how the third and the fourth law are better explained. So now with law number 5, I want you to tackle it or think about it while keeping law number 3 and 4 in mind, right? So remember with law number 3, we said if we had something like this, and obviously it's raised to the power of x, we're going to get a product like a to the power of x multiplied by b to the power of x. And part of the reason this is the case is because remember, if we write a, it's the same as a to the power of 1, and obviously this will be the same as b to the power of 1. So this x is basically multiplying this exponent, and it's also multiplying this exponent, and this is the value that we're going to get, right? So with law number 5, it's kind of the same concept, but in this case, it's not a to the power of 1, it's a to the power of any number. So any number can be represented by a variable, let's say a to the power of n, right? So if a to the power of n and we multiply it with that bracket, the value or the product of those, it will be a to the power of n times m. So it's kind of the same concept with law number 3, right? It's kind of the same concept with law number 3. It's just that with law number 5, obviously in this case, a is not raised to the power of 1. It's raised to the power of a certain variable, which can represent any number. So I just want you to keep that in mind. Law number 3, 4, and 5, they kind of mean the same thing. It's just that I don't know. They kind of explained in a bit of a different way, but they're more of like the same family, if I could put it like that. So with law number 6, we're basically saying any value that is raised to the power of 0 Keep in mind that value can't be 0. So a represents any value outside of 0, right? So any value that's raised to the power of 0 will always give you the value of 1. It will always give you the value of 1. So that's law number 6. It's very simple. Just know that any variable that's raised to the power of 0 will always give you the value of 1. So law number 7. This one is a pretty interesting one, and you're probably going to see it very often when you're doing exponential expressions, right? Because in many cases when you're doing exponential expressions, you're probably going to be told that you need to leave your answer in surd form or with a positive exponent. So we have a law that says if we have something raised to the power of a negative value and we need to obviously leave that in positive exponents, what we need to do is take that whole power and obviously put it on the denominator and obviously change that negative to a positive. So that's the only thing that you do. You take the whole power, you put it on the denominator, and obviously in this case you'll have 1 left at the numerator, and you just change the value of that exponent into a positive value, right? So a good example would be this. Let's say, for example, we had something like 2 multiplied by a to the power of 3, right? Negative 3 in this case. Let me just say negative 3. How would you rewrite that, or how would you solve that? If we had a terminology like this, let me use multiplication so that you can understand, you can see it clearly. So in this case, if we were to leave this answer in exponential form or in positive exponents, what we would do is we'd leave the 2 on the numerator, and obviously this power here, we're gonna put it on the denominator and change the value of and change the sign of the exponent in this case, and obviously that would be a to the power of 3 instead of a to the power of negative 3. So keep in mind with this, you're probably going to use it more often because in many cases, as I've already stated, when you leave your answers, you need to leave them with positive exponents. In many cases, that's what's stated. And also on that note, let's say, for example, we had something like 1 or over a to the power of negative m. So if we have the inverse of what we're already given, in this case, you do the opposite. You have to leave that as a to the power of m. So you take it obviously to the numerator and you change the sign. So that's just what I want you to keep in mind with this law. It's such a simple law, but a lot of people kind of miss it. So just keep in mind, every single time you have a negative exponent in the denominator, you just take it to the numerator and change the sign. And obviously if you have a negative on the numerator and you want to make it positive, you just take it to the denominator and change the sign. So that's basically it with this law. So the last thing that I really wanted to talk about, I don't know if this is referred to as a law, but the last thing that I really wanted to talk about is this. Let's say, for example, we had an expression like a to the power of m over n, right? What does this mean? What does this mean? I really want you to get a sense of what this means. So this basically means that here, if we look at the exponent and we focus on the denominator, that denominator obviously it's dividing m, right? But if we were to rewrite that, we just say the square root of a to the power of m, and obviously we're going to put our n there, right? So let's just use a numerical example so you guys get to see how that's being applied. So we know that 2 to the power of 6 over 2, that will give us 2 to the power of 3, which is 8, right? But if we were to rewrite that, we just say the square root. The reason why it's a square root is because on the denominator it's 2, it's 2, and we're going to say 2 to the power of 6, right? So now we know that 2 to the power of 6 is the same as 64. 64, and the square root of 64 is 8. So it still gives you the same value, right? So let's just do another example so that you can kind of better understand it. So let's say, for example, instead we had something like 2 to the power of 8 divided by 4, right? We know that that will give us 2 to the power of 2, right? So if we were to rewrite that, we just say that will be 4, and this will be 2 to the power of 8. And obviously, I don't know how you solve this or what 2 to the power of 8. 2 to the power of 8 is, that will give you 64. I think that's 128. 2 to the power of 6 is 64, 128, 256. So this will be 256. And 256, if you, I don't know, is it cubing? It's not cubing it. I don't know what it is, but if you think it, you'll probably get the value of 4. You'll still get the same value of 4. So that's one thing that I wanted you to keep in mind as well. The last thing that I actually wanted to discuss with you when it comes to laws of exponents. So that is it for this video. In the next video, we'll be doing a couple of examples applying these laws of exponents and see how questions are often asked. So that's it for this video. Please don't forget to share, like, and subscribe, and tell your friends about it. Comment if you really want us to add something, or if there's a topic that you really want us to discuss. And hopefully in the next video or in the future videos, we'll be able to discuss that. Cheers.